Hello, everyone. My name is Mahar Al-Asfar. I'm a senior technical marketing architect focused on Aria Automation at VMware within the Cloud Management Business Unit. In this demo, we will leverage the Cloud Consumption Interface, CCI, powered by Aria Automation and vSphere Plus subscription, to deploy a two-tier e-commerce Kubernetes-based open source application called Opencart. For instructions on deploying the application fully from the command line and access to the Kubernetes YAML manifests, scan the QR code on the screen to access the GitHub repo. In this application architecture, the backend database tier consists of a virtual machine running a MySQL database and a load balancer service exposing both MySQL on TCP port 3306 and SSH on TCP port 22, all while leveraging the VM service and the VM operator. The VM service and the VM operator within vSphere with Tanzu uses a declarative Kubernetes custom resource definition VM provisioning approach and an automatic load balancing service across multiple VMs, in addition to an industry-standard Cloud Init-based guest OS customization, all along with administrative controls for things like VM images and VM classes for the vSphere administrators. The front-end web tier will consist of a Kubernetes pod and a load balancer service exposing HTTP on TCP port 80, deployed via a Bitnami Helm chart package with a custom set of parameters in the default namespace of a TKG workload cluster. The provisioned virtual machine and the TKG workload cluster will run within a dedicated supervisor namespace on a supervisor cluster. The front-end pod will connect and use the MySQL VM as its backend database via the database load balancer service. And finally, the consumer can load the e-commerce website by connecting to the front-end load balancer web service via its IP address. To summarize, and before we begin, in a numerical order, we will first provision a supervisor namespace. We will then provision a virtual machine running MySQL and its load balancer service, and then move on to provision a TKG workload cluster, then deploy the front-end pod and its load balancer service, and then finally connect to the e-commerce website application, all leveraging the Cloud Consumption Interface, CCI. So let's get started. Developers can log into the VMware Cloud Service portal and launch VMware Aria Automation to build and manage modern applications via the Cloud Consumption Interface, a simple self-service consumption of Kubernetes via a unified interface for both on-demand infrastructure and containers provisioning across VMware-based cloud, enabling authentic DevOps experience available through a consistent open command line interface, APIs, and a cloud-like UI to interact with for all cloud and IaaS services and operations. We will start by clicking on Aria Automation Service Broker, where the developer can request resources and services by being a member of one or more Aria Automation projects. On the overview landing page, we have a Getting Started sections to help you get familiar with new key concepts and how they all work together. We can also see that the developer in our demo is a member of the supervisor project. You can also download the CCI CLI plugin from the overview landing page. If the developer is a member of multiple projects, we can filter and select the project we want to create resources and services for. Since all user-managed vSphere supervisor IaaS resources get created within the scope of a supervisor namespace, we must create a supervisor namespace first. Click on the supervisor namespace menu item to create our first supervisor namespace within the supervisor project. Since there are no existing supervisor namespaces yet, we are presented with a Getting Started with Supervisor Namespaces page to guide us through the process and display information on a couple of key concept topics. In addition, the ability to download the CCI CLI plugin and a link to the official documentation to learn more on CCI. Click New Namespace to create a new supervisor namespace within our project. We can pick a predefined namespace class from the one available to our project. Think of a namespace class as a template created by the cloud admin to define specific namespace settings such as what storage classes, VM classes, content library sources, and resource quota limits to use and configure when a supervisor namespace is provisioned from a namespace class. Click Create on the namespace class available here called Basic. We will type Opencart as the name of the supervisor namespace we want to create against the on-prem region that the project can access. A region is a group of supervisors bound to projects to allow it to access the supervisors within, again defined by the cloud admin depending on the organization infrastructure requirements. VMware's recommended best practice is to have similarly configured supervisors within a region so that namespaces can be placed anywhere within the region and have similar capabilities. Notice that the project is configured by default to share the created namespace with all project users. We can disable the sharing at the project level if we don't want to share deployments with all project users. Finally, click Create. In summary, the user doesn't need detailed knowledge of the infrastructure behind this. Instead, the user chooses a namespace class and then decides on a name and region for their supervisor namespace resource. Once created, we can click on the supervisor namespace Opencart to access the supervisor namespace summary page and all the services available to the developer. Next, we will click Open on Virtual Machine and click on Create VM to create our backend MySQL database virtual machine. We'll provide the VM name and select Ubuntu 18.04 as the server cloud image we want to use. The list of VMs images displayed here depends on the supervisor namespace class used to provision the Opencart supervisor namespace. Next, we will select our VM class as best efforts small, which will configure our MySQL database virtual machine with 2 virtual CPUs and 4 GB of memory. Again, the list of VM classes displayed here depends on the supervisor namespace class used to provision the Opencart supervisor namespace. Notice the generated YAML manifest for the virtual machine gets populated based on our selection. We also have the option to use advanced settings such as persistent volumes, SSH public keys, and more. For our demo, we will configure a load balancer to expose MySQL on TCP port 3306 and SSH on TCP port 22 as virtual machine service that will allow the load balancer to route traffic from the source ports on the load balancer to the external ports on the virtual machines running the service. Again, the generated YAML manifest for the load balancer gets populated based on our settings. Finally, we will use the Cloud Config section to specify any data, configurations, or scripts to initialize and configure MySQL on our virtual machine on the first boot. Cloud Init is an industry standard to help set up things like networks, storage devices, configuring SSH access keys, creating users and groups, installing packages, and setting up our applications. We will click Next to review the final configuration and the generated YAML files in the viewer for what we are about to provision. Notice here that the user can copy or download all the YAML files and use them to create the same objects or modify them to create new object from the kubectl CCI plugin command line. Let's click Deploy VM to deploy our virtual machine. Once the VM is ready, we can click the double arrow to expand the VM details or click the VM name to view the summary page and execute day 2 operations such as changing the power state of the virtual machine or attaching additional disk volumes, increase capacity on existing volumes, or detach volumes altogether. Click the YAML tab to view the actively generated YAML for the virtual machine. Clicking the top navigation menu returns us to the Opencart supervisor namespace summary page. Due to our previous database VM provisioning workflow, we can now explore the network service by clicking Open to display the created load balancer service. Clicking the network service name displays the network service details within the Summary tab, especially the external IP of the database service that the front-end web Kubernetes pod, once deployed, will be connecting to. Clicking the navigation menu again returns us to the Opencart Supervisor Namespace Summary page. Next, we will click Open on the Tanzu Kubernetes Grid service and click Create to deploy a TKG workload cluster, a fully upstream compliant Kubernetes cluster that we will use to deploy our front-end web pod and a web load balancer service via the Bitnami packaged Helm chart later in the demo. Here you can choose between the new cluster class API or the original Tanzu Kubernetes cluster API as the cluster type. Use the cluster class API to deploy the Kubernetes cluster using built-in cluster class object definitions, which happens to be the newest cluster API for all new Kubernetes cluster creations as we go forward. Use the Tanzu Kubernetes cluster API to deploy the Kubernetes cluster using the Tanzu Kubernetes cluster object definitions provided for backward compatibility and a legacy offering. The Tanzu Kubernetes cluster API is to be deprecated in future releases. Both types for now are supported cluster types that you can choose from. We will choose the Tanzu Kubernetes cluster and the custom configuration in this demo to create our TKG workload cluster. Clicking Next, we will set our cluster name, choose our Tanzu Kubernetes release, and determine if we want to provide our custom network ranges or select the container network interface type we prefer. We will use the default ranges for both pods and services for now. Then select the storage available within the Opencart Supervisor namespace and set it as our default storage class. Notice the generated YAML manifest for the Tanzu Kubernetes cluster getting populated based on our settings. Next, we will define our control plane by specifying the number of replicas. We will keep it to one master for now and select best effort small as the VM class. This will configure our control plane VM, our master, with 2 virtual CPUs and 4 GB of memory. Next, we will click Add Node Pool to configure the worker nodes. We will provide a name for the node pool and keep everything else as default. This node pool configuration will create one worker node configured as best effort small using the storage class available within the Opencart Supervisor namespace. You also have the option to define labels and if you would like to configure volumes at this stage. We'll click Next to review and confirm our configuration and then click Finish to finalize the node pool configuration. You can create other user node pools to support applications with different computing and storage demands. We will now click Next to review our final configurations and the generated YAML files in the viewer for what we are about to provision. Notice here that the user can copy or download all the YAML files and use them to create the same object or modify them to create new objects from the kubectl CCI plugin command line. Click Finish to deploy our TKG workload cluster. Once the cluster is ready, we can click the double arrows to expand the cluster details or click on the cluster name to view the summary page for more information and also to execute day 2 operations such as editing the control plane and node pools configuration. To scale out or scale in by changing the number of replicas, or scale up or scale down by changing the node's VM class. Also view the actively generated YAML for the TKG workload cluster by clicking the YAML tab. And then clicking the top navigation menu to go back to the Opencart Supervisor namespace summary page where now we can explore the network service again by clicking Open to display the additional Kubernetes API load balancer service. Before we deploy our application, let's look at what the VI admin would see on the vCenter server side based on the developer IaaS consumption via the cloud consumption interface. First, we see our Opencart Supervisor namespace, which if we expand, we know that it contains both the MySQL VM and the TKG workload cluster with its master and worker nodes. Most importantly, the supervisor namespace is configured based on the supervisor namespace class that we chose to configure things like what storage policies to use, what VM images and classes would be available within the supervisor namespace. Also notice that the developer who initially requested the supervisor namespace has owner permissions. At the same time, the project members, on the other hand, have been granted edit permissions since the cloud admin configured the project to share supervisor namespaces across all project users. Let's now explore and use the kubectl CCI plugin command line to log into the cloud consumption interface. The developer can first generate a Service Broker API token from the Cloud Services Portal UI based on their user service role to log in using the CCI CLI plugin. When successfully logged in, kubeconfig contexts gets automatically created for the developer to access based on their project membership. When using the CLI, the Cloud Consumption Interface Cloud Layer Kubernetes API server is listed as a kubectl context after logging in. CCS is the kubectl context used to list projects, regions, and supervisor namespaces in each project. It's also used to self-service creating new supervisor namespaces, virtual machines, and TKG workload clusters via the CLI. CCS Supervisor Opencart is the kubectl context that gives the developer CLI access to the supervisor namespace with communication proxied appropriately to the underlying supervisor without the user needing to log in more than once or worry about their network connectivity to the underlying vSphere supervisor. We will set our CCS Supervisor Opencart in our demo as the default context. The supervisor is the project name, and Opencart is the supervisor namespace within the project as we know, both represented in the CCS context name. Now we can query our resources or create new ones with the Opencart supervisor namespace. Here we execute the kubectl command to query our Kubernetes VMs, VM service, and service objects, and we see all the provisioned VMs, including their power state and the image and class used, and the assigned primary IP addresses. We also see our DB load balancer service, which has an external IP of 192.168.123.3 that we will use to connect our front-end web pod to the backend database. We can also query our TKG workload cluster by running kubectl get tkc, among other things. Here we see that our cluster OC-DKG-cluster has one control plane and one worker node, running Kubernetes version 1.23.8 and is in a ready state. Let's now log into our TKG workload cluster using the kubectl vSphere plugin command line. Here we pass parameters such as the supervisor FQDN or IP address, the Tanzu Kubernetes cluster name, the Tanzu Kubernetes cluster supervisor namespace, and our SSO username. Next, we will set our TKG workload cluster as the default context so we can deploy our application. Tanzu Kubernetes Grid Service provisions Tanzu Kubernetes clusters with a pod security policy admission control enabled by default, which means that a pod security policy is required to deploy any workloads. The following command creates a cluster role binding that grants access to authenticated users to run a privileged set of workloads using the default PSP or pod security policy, VMware-system-privileged. Not something that we recommend doing in production, but for the sake of the demo, as a quick start, it will allow deployment of the privileged workloads cluster-wide. Since we will be using Helm chart packaged by Bitnami by VMware to deploy our application, we will add the Bitnami Helm repo first. Next, we can use the Helm install command to install our Bitnami Opencart with a set of parameters, including the backend MySQL database service IP as our external database host. Next, we simply follow the provided Helm chart template instructions, where first we run kubectl get service command to get the front-end web load balancer service IP. Here we can see that it was assigned IP 192.168.123.5. We then run the provided export commands to set variables like app_host and app_password used by the following command. Then we complete our Opencart deployment by running the Helm upgrade command while passing the variables we set previously. When executed, it deploys our front-end pod with its web load balancer service. We can then run the kubectl get all in the default namespace on our TKG workload cluster to ensure our front-end web deployment, pod, and service objects are running. Finally, we can switch to our browser and pass the URL to our application to load our e-commerce website. That's it for this video. I'll see you in the next one, and thank you for watching.